This lesson covers properties of functions for secondary 3 math. In the first part, it's going to talk about independent and dependent variables as well as inverse. And because it's so long, that's why there are two parts. This is a pretty long lesson. The second part is going to cover domain, range, variation, sign, so positive, negative, and the extrema, as well as the intercepts. So first, a recap. You need to remember that functions are a type of relation between two variables, usually x and y. When we label them x and y, they correspond to their respective axes on a Cartesian plane, the x and the y axis. Functions can look straight, they can look curved, so long as they pass the vertical line test. Let's just look at the plane for a second just to recap everything. So here's our Cartesian plane, and it's super important that you remember what axis is which by heart before we discuss anything. So you have your x-axis and you have your y-axis, okay? And you also need to remember that you have your origin, also known as 0, 0. Now, you've already seen this before, but let's recap. Your independent variable is always the x values, and your dependent variable is always the y values. When we're talking about word problems, usually it's up to you to find what is the x and what is the y. Sometimes x is time, sometimes y is time. It's up to you to check this out. So my example for you is painting a room. The time it'll take to paint a room depends on the size of the room, which makes sense if you think about it, right? The bigger the room, the longer it'll take for you to paint. The smaller the room, the less time it'll take for you to paint. So there's definitely a relation between painting a room and how big it is, right? So in this case, x is the size of the room because the time it takes depends on the size. It's weird, I know, in this case, because usually you're used to y being time or x being time. In this case, it's not, okay? So this is also an exceptional exception. Now that you remember what x and y is, independent, dependent, let's talk about what the inverse of a function is, okay? Simply put, very simple. The inverse of a function is when you have a set of values, so you have your x values and you have your y values, and you just flip them. So x becomes y and y becomes x. So here's a relation. You have your x's, you have your y's. Simple, 030s, 370, so on. Okay. The inverse of this relation is when you're literally just taking your y's and putting them in the x box, and you're taking the x's and you're putting them in the y box. So see, literally I'm just flipping them. Okay, that's what the inverse is. Let's look at it a little bit more specifically though on a graph. So here is your original relation, and here is the inverse of the relation. But what is really important for this chapter is that you need to determine a lot of the times if the inverse is or is not a function. So relation A was a simple function. You'll see this if I do the vertical line test. Boom, I'm good. I'm honestly good. It looks weird down here, but I'm good. If I do the vertical line test for the inverse, you'll see that it is still a function. So a question could be like, is the inverse of a function? Yeah, it is. Okay. Now, this is also on a graph. Sometimes you won't be given a graph. Sometimes you'll be too lazy to even draw a graph, so I'm going to show you ways where you can tell when an inverse is not a function besides using the vertical line test. Okay. So here's relation B. You have x's, you have y's, and we're going to flip them so that we can check out the inverse of relation B. I just want you to look at this for a second and recall some of the things that I've said to you in the past or that you've heard in the past. What makes a function, especially in a table of values? Well, if you look here, you have 2, 10, 4, 14, 6, 7, and here you have 10, 2, 14, 10, 6, and then, okay, look at this. Right away, your math senses should be tingling because a function cannot have repeating x values. And here the inverse has a repeating x value of 10. So before we get to the conclusion, let me graph it so that you can actually see it. Okay, here it is. You can guess that original relation B is blue. So vertical line test checks out. But inverse relation B is red. For a reason too. If I do the vertical line test, it fails. You'll see this because I'm crossing through it so many times, including point G and E, which both have 10. Okay, so in this case, the inverse of relation b is not a function. Our tingling math senses were correct. So now I want you to just try it yourself. So are the inverses of the following a function or not? So here are your two examples. Take a second, check it out, tell me what you think. In this case, the inverse is a function. If we assume that the table stays like this, okay, if we assume that the table stays like this, the x's won't repeat. If we inverse the function, the inverse therefore is a function. But in the second case, can we check it out, the vertical line test? If we plot the points on a table of values, okay, you have 14, 3, 15, 6, 16, 5, 25, okay? So if we were to flip these, this is the original, right? If we were to flip these, you'll notice that the 5s would repeat in the x boxes, and so therefore it is not a function. And if you want, you can take the time to graph it, and you'll check vertical line tests, it won't work. But you could just easily put it on a table of values. You'll see right away that your x values repeat. As we end part 1, I just want to recap. X values are known as independent and Y values are known as dependent, and sometimes you're going to have to figure out in a word problem which is independent, which is dependent, and you need to know where the X and Y axes are on the Cartesian plane. You also need to understand what the inverse of a function is, and it can be found when you invert, not a clever name, you invert, you flip the X and Y values of a function. You remember that on a table of values, the function is, it's not a function, sorry, when the x values repeat. And if you would like to double check on a Cartesian plane, the vertical line test will easily tell you if this is a function or not. Moving on to part 2, we're going to strictly look at the properties of functions. Now there are several of them. They're not difficult, but there are several of them, and I think that's what's more confusing. But we'll take this one property at a time. Every function has certain characteristics or properties that define it. We will be looking at 6 different types of properties of functions. But before we actually look at different functions, we're going to look at different properties. When you will be introduced to different types of functions in the next few weeks, you will be able to, or you need to be able to identify the following 6 properties for each function you were introduced to. Beginning with domain. Domain deals with x values. The domain of a function is all the x values of that function. To identify this property and several others that are on their way, you will be asked to use interval notation or square brackets. You will also need to look only at the x-axis for this property. You only need to care about the x-axis for this property. So here's a function on our Cartesian plane, and all these properties you need to identify using a Cartesian plane, not table of values. You will be given a Cartesian plane. So here's a function. The domain of the function is all the x values of the function using interval notation. So if you're looking at this beautiful graph here, assume it starts here and it just goes shunk up here. All right? So we don't care about these right now. We do not care about these right now. And let's see if this pen works. This here, yeah, this here we don't care about, so we're just going to hide it for now. Okay, now, if we look here, it starts at 0 and it ends at 3. So the domain of this function is 0 to 3. If we use square brackets, it's including 0 and including 3, and we write our comma in the middle. Now, that was easy because it started and it ended at certain points. You saw it, it was no big deal. But now let's talk about what happens when a function goes on forever. Okay, because we've seen that. Functions go on forever sometimes, right? In our case here, we are only looking at the x-axis. And you'll notice that we don't know where it starts and we don't know where it stops. So it's basically infinity to infinity. So it spans from negative infinity to positive infinity. So how do we write this in interval notation? We write that the domain of this function is from negative infinity to infinity, and you need to remember that when we deal with infinity in interval notation, the brackets always face away from infinity because it goes on forever. So the brackets cannot be hugging, they have to be away. Now that we've talked about domain, which was just the x values, we're now going to talk about range. Range now is like domain, but only the y values. In this case, we look from bottom to top. So look from the bottom to the top of the function, okay? So kind of tilt your head sideways, if you will. And again, you need to use interval notation. Here's another function, or actually here's the same function, sorry, on the Cartesian plane. Now, in the first one, we looked at just the x values. In this case, we're going to look at the y values, okay? Now, tilt your head, bottom to top. Starts here, ends here. Starts at 10, ends at 73. Starts at 10, ends at 73. In this case, the range of this function is close bracket 10 to close bracket 73. 10 to 73. Closed dot here, so we include it, right? Closed dot, and assume there's a closed dot here too. Just because of the context of this question, we assume that it's a closed dot, okay? So closed brackets 10, 73, and that's range. Same example with infinity as we did with domain. Again, we don't know where it begins, where it ends, but it goes on forever, okay? So if you look bottom to top, range of this function is from negative infinity to infinity, and remember, brackets face away. Simple as that. Before I move on, is it possible that you're going to have infinity and a number? Yeah, absolutely. You could have one that goes from infinity to a number or a number to infinity. It doesn't matter as long as you remember that it's possible that it goes to infinity or that it starts at infinity and brackets face away. So now I would like you to try this yourself. So please find the domain and range of the following functions. Here is function number 1. Here is function number 2. Take a second, pause this video if you have to, find the domain and range of the following functions. In this case, if we look at the domain from the x values, we go from -4, but I don't know where it ends. So it's going to be hugging -4 all the way to positive infinity. And your range, well, again, bottom to top, right? So we don't know here, down here, we don't know where it begins, where it is. So negative infinity, but we know that it ends at 3. So negative infinity to 3. And in this one here, your domain, well, I don't know where it stops or ends if I look at my x-axis, so it's from negative infinity to infinity. And my range, well, I don't know where it starts, but I know that it ends at 1. So it'll be from open bracket negative infinity to close bracket 1. Now we're going to talk about what variation means when your function is increasing, decreasing, or constant. And for this property, we are only going to look at the x values. A function can be increasing, decreasing, and or constant throughout the Cartesian plane. So it can be all of these, none of these, one of these, two of these. It is increasing when the function moves towards the top of the plane. Easy enough, right? It just goes this way. It is decreasing when it moves towards the bottom of the plane. So again, easy, goes in this direction. And it is constant when the function moves in a straight horizontal line on the plane, so straight across. All right, so here's an example. Like domain and range, we're going to use interval notation, and like domain, we look at the x values only. I don't care about the y values for this. For any property that deal with x values, read the graph like a book. You read a book from left to right. So we start here, we go here, we go here, we go down here. Okay, so follow my arrow. So this function starts, it increases from 0 to 3. Again, x values, not from 0 to 200, 0 to 3. Then it becomes constant here from 3 to 10, okay, looking at your x values, and then it decreases from 10 to 15. So if we were to write this all fancy, it's increasing, close brackets 0 to 3. It's constant from 3 to 10, and it's decreasing from 10 to 15. Always close brackets. Okay, always close brackets, even though I know how can it be increasing and constant? Well, it can. It's actually increasing and constant at the same point 3. It's actually constant and decreasing at the same point 10. So always close brackets unless you see an open dot or infinity. Now, let me give you an example with infinity and what we call the union, which I know that you've probably seen before. So in this case, the function on the left increases and it decreases, but there are no constant. So if we read the graph from left to right in words, the function begins here. It increases, it decreases, and then increases again. And just to give you a more visual, I've labeled it out with you with arrows. So arrows pointing up, increasing, arrows pointing down, decreasing, arrows pointing up, increasing. Also note that the function doesn't start or stop at any particular point because it spans infinity. Let's talk about how this function goes. It's increasing from negative infinity to negative 1.73. Remember, not 10.39. We are not looking at the y values. So it increases from negative infinity to negative 1.73. But you'll notice it increases again from 1.74 to positive infinity. And it decreases just in this interval here, so from negative 1.73 to 1.74. So how do we write this in fancy interval notation? So in proper interval notation, we say that it's increasing from negative infinity, open bracket, negative infinity to negative 1.73, close brackets, union, because there's another instance, 1.74 to positive infinity. You could literally have like 5 different increasing intervals as long as you union them. So union means, or the U means union, or you could see it as and in this case. And the only time it's decreasing is from negative 1.73 to 1.74, close brackets. Keep in mind, not all functions increase and decrease. Sometimes functions just increase. Sometimes functions just decrease. Not all functions have a constant interval. Sometimes they do. Sometimes they don't. Okay, it's okay. The next property we're going to look at is sign. It's kind of like variation, but it deals with when your function is positive and when it's negative. Again, only looking at the x values. The sign of a function is when it is positive and when it is negative. And a function is positive when it is above the x-axis. A function is negative when it is below the x-axis. We look at the x values only, and we also use interval notation for this property. Keeping in mind, not all functions are negative. Sometimes functions are only above the x-axis. Sometimes functions are below the x-axis. It's possible for you to have functions that are positive and negative, just positive, just negative. So let's look at an example. With a union, since you should be familiar with this by now, so we read the graph from left to right, and in words, the function begins negative because it's below the x-axis. See here? Then it becomes positive again. Or again, it becomes positive. It crosses the x-axis here, becomes positive, and then it crosses the x-axis once again, and it finishes negative. So using this as a union, we say that it's negative from 0 to 10, not from 150,000, from 0 to 10. And then it's negative again from 30 to 35. So we do 0, 10, union, 30, 35. And the only time it's positive is from 10 to 30. That's it. Okay, interval notation, x values only. And again, with infinity, in words, this function first begins negative, then crosses the x-axis as negative 3, becomes positive, then crosses the x-axis at the origin, becomes negative again, and then crosses the x-axis again at 3 and becomes positive. To help you out, positives and negatives. Okay, so kind of like what I did with the arrows, I'm doing it with positives and negatives. So it's easier for me to visualize personally. It's negative. Negative infinity to negative 3, union 0 to 3. This is the 2 instances where it's negative. And it's positive here, first instance, from negative 3 to 0. Remember, x-axis. And then again, it is positive from 3 to infinity. So just check it out here. So 2 points when it's negative with a union, 2 instances where it's positive with a union, looking at x-axis only. Your turn. Identify the sign and variations of the following functions. So the same 2 functions I gave you earlier, only this time tell me when they are positive, when they are negative, when they are increasing, when they are decreasing. Keep it in mind, some don't increase, some don't decrease, some are positive, some are negative, doesn't matter. Take a second, try it out, and then check your answers. So for the function above, it is never increasing, actually, never. It starts here and goes right down. So it's decreasing from negative 4 to infinity. Remember x values. It is positive from negative 4 to 1, and then it crosses down here from 1 to infinity. Now see here, I opened my bracket. Did I need to open my bracket? No. So change this to a closed bracket, actually. It is included. Okay, assume that is included. And the 1, of course, is included to infinity. Down here, we have 3 instances of variation, increasing from a negative infinity to negative 1, then constant from negative 1 to 1, and then decreasing from 1 to infinity. Okay, and then it's negative down here, so 2 instances from negative infinity to approximately negative 1.5. And then it's again negative at positive 1.5 to infinity, so unions, because there's two. And then it's positive from here, so negative 1.5 to 1.5, and so I write it like this. All right, we're going to talk about the last two properties. We're almost there. Your extrema, so the minimum and maximum of your function. We're only looking at y values here. In this case, we look at the y-axis, and I basically just want to know how low and how high the function goes. No interval notation for this, okay? It's just a number. And if you want to know how high and how low your function goes, check your range. Where does your range start and end? Okay, super important. If a function begins or ends at any infinity, okay, the min and max does not exist. The min and max can only be a specific number, okay? One number for min, one number for max. Infinity does not count as a number. So if we have infinity as our max or our min, we do not put it. We put DNE. So here's an example. So again, no interval notation, just what's the number? What is the highest point of the function? And what is the lowest point of the function? So I've drawn out lines here so that you can see the highest point of the function here is at 18 and the lowest point of the function is 4. So we just write that the max is 18 and the min is 4. Done. That's it. Okay? No infinities, just numbers, so we have a min and a max. But when we do have infinity, we're looking from bottom to top if we look at our range. So it starts at negative 10.39 on the y-axis. So it starts down here, right, because we're going from this to this. We don't see where it finishes. Okay, so it goes on to infinity. So we know that the min is at negative 10.39, but because it goes to infinity, the max does not exist. DNE, none, nothing. Okay, do not say that the maximum is infinity. I will mark you as incorrect. Now, finally, the intercepts. You already really know one of them, but we'll talk about both. There are two different kinds of intercepts. The first one you should be very familiar with is the y-intercept, or the initial value, where the function crosses the y-axis. It can be found visually just by looking at the graph, or you can find it algebraically by making x equal to 0 in whatever function rule you're given. Then you have what's called the x-intercept, or the zero of the function. The zero, when I ask you for the zero or the zeros, it's where it crosses the x-axis. There can be many zeros. In a function, there's usually one initial value, but there are many zeros. In this case, a zero can be found visually just by looking at the graph. You can see where it crosses the x-axis, or algebraically. But in this case, instead of making x equal to 0, you make y equal to 0, and you can solve for your zeros. So here's an example. So visually, I can see here that there are two zeros and one initial value. No interval notation for this, kind of like min and max, except it's encouraged that you could maybe use curly brackets. In this case, the y-intercept is negative 3. So we put curly bracket negative 3, but there are two zeros. It crosses the x-axis at 3 and 9. So we just write 3, 9. It's possible that sometimes you only get 1 0, but in this case we have 2. Now, I want you to find the min and max and the x and y intercepts of the following functions that I've given you here. Keeping in mind, okay, min and max could be none, could be some. Your intercepts could be some x-intercepts, could be one x-intercept. Pause this and try it yourself. Here, the max is 3, y values, and the minimum does not exist because it goes to infinity. Your y-intercept is 2, and there's only 1 0, it's 1. And down here, your max is 1, but your min goes to negative infinity, so it doesn't exist. Your y-intercept is 1, and you actually have two zeros, negative 1.5 and just 1.5. So for your pleasure, I have given you this, and in class I will give you a paper copy of this. This is like your cheat sheet for your properties. Here they all are. Domain range. So domain, all x values. Interval notation, x-axis only, left to right. All the y values of a function for range. Interval notation, y-axis only, from bottom to top. And so on for all of these. Okay, so this is your recap page. Keep this Very close. I tell you what to do and when, and it pretty much outlines every single property. And that is the end of properties of functions.